Today I'd like to share with you about the work kinetic energy theorem, how work is a force times a displacement, and that's going to be equal to the change in kinetic energy of an object, of a mass. So this relationship here, force times displacement equals change in kinetic energy, it's an equality, so that means we should somehow be able to convert from a force and a displacement to a change in kinetic energy, which would look like 1/2 m final velocity squared minus 1/2 mass times initial velocity squared. That's the change in kinetic energy. So where does this come from? Well, let's start with the beginning, force times displacement. A force in itself is a mass times an acceleration. So we now have mass times acceleration times displacement, same as force times displacement. An acceleration itself is a rate of change in velocity. Got my symbol mixed up. So change in velocity over change in time. And then we have this delta x out here. So there's a lot of change going on, as you see. Well, as an object accelerates, it doesn't just move at a constant pace. So what values can we substitute in here to possibly bring about this change? Well, you might start to see that the change in velocity is a VF minus a V0. So the question is, where's the squareds come? Where's the half come from? Well, we go to a few definitions here. Delta V over delta T, just to expand it out a little bit, would be a final velocity minus initial velocity. And instead of a change in time, I'm just going to write T because an initial time is usually 0. So we do have this form. Well, what about this delta X? Well, when an object accelerates, you might say it has an average velocity when it goes from an initial value to a final value. So to find the average of any two numbers, as long as it's a constant rate of acceleration, we have initial velocity plus final velocity over 2, just like you'd take an average for any two numbers. Well, velocity is also defined as a change in position or displacement over a change in time. So we're left with here something very usable, because if we solve for the displacement, we find that the displacement is equal to VF plus V0 over 2 times delta T, or just T, as we're going to see later on. So delta, let me clear that up a little bit. Delta T. There we go. Now if we substitute this guy and the fact that delta V over delta T is this amount, so we're going to substitute these two, and notice these are two components here, right there, and there's a delta X right there. We're left with now M times VF minus V0 over T times, now all this comes in here, VF plus V0 over 2 times T. So I'm dropping the delta that's over here. And let's clean this up a little bit. We're starting to see something up here. We've got the T here in the numerator and the T over here in the denominator. Those two will cancel out. And we got this 2 hanging in here, so I'm going to place that under the mass. And then we've got a VF plus VF minus V0 times a VF plus V0. Now if you distribute these two, we'd have VF squared plus VF V0 minus VF V0 minus V0 squared. So all this is M over 2 times VF squared minus V0 squared. And if we take a look at that and distribute the M to each one, and we've got a 1/2 sitting out here, we end up with 1/2 MVF squared minus 1/2 MV0 squared. That agrees with our change in kinetic energy. So force times the displacement does equal a change in kinetic energy.